All right, we're back recording. I got my camera over here set up. So just very short announcements. You have your homework is due tonight at 11. There's apparently a couple people thought it was due Wednesday, probably because I kept having the last 4 or 5 of them were due Wednesday as well. But this one is due tonight. I'm thinking there'll be one more short homework before the exam, which will be next Friday. So that means we have 3 kind of main sections. We've done all the microwave network theory, the impedance matrix, scattering matrix kind of stuff. Then we did the matching network. So you have the lumped element, and then there was the series shunt stub kind of matching. And then we'll have one last little bit of stuff next week where we're going to just focus on doing Smith charts by hand solutions. And then a binomial matching network. Maybe I'll squeeze in a Chebyshev while we're at it, but I will probably just test you on the first one. Something like that. So that'll be pretty straightforward. I think the first 2 sections are really going to be the most interesting. The multi-section matching network stuff is interesting, but most classes like this tend to just sort of skim over it a bit. Because I think the series and shunt stub stuff is a lot more, what's the word, instructive, I guess. The multi-section networks are useful and all, but like you get that mixed benefit of being able to use the Smith chart when we're doing the other series and stub matching network kind of stuff. So there'll be kind of some token treatment of that on homework. I don't know if I'm going to test heavily on that. There might be like a simple question or 2 of just like design a 4-section binomial matching network where you just have to calculate 4 little impedances, that sort of thing. But those will be pretty strict. It's the other stuff though really is going to be the bulk of the exam. So I think there was a couple of questions as far as the homework was concerned. So I was going to say, let's take maybe 5-10 minutes to go over that. And then I'm just going to do some Smith chart practice over here. You notice I even wrote down the recipe so I don't screw up a step. So I got all the way to about here last time before I mixed up my last steps there. So I apologize for that. So I really want to go over that and clarify in class. So feel free to jump in if you have a question on the homework that's giving you trouble. I was going to say, let's just kind of go over that right now. Or I can just kind of do what we normally do, where we just go problem by problem and walk through the steps, if that's a little better approach. Chad, I'm looking your direction. You're the one who had the questions, right?
I think if you just went problem by problem, it'd probably help, because that would probably answer any question I had. So
okay, let's do that real fast then. So I'm going to share my screen. So here is all of the problem set here. So if I remember correctly, I did pretty much all of this stuff Monday. We kind of walked through and I wrote the code and uploaded it for you. And so the idea was you really just should have had to tweak a few bits of that to get this section to work. And then also for the lab, we walked through that, but I wanted you to try and modify the code to do your lab. So if you were able to get your jumpstart on the lab, you should be able to do the last problem in this set as well. So it kind of looks like a lot, but there's just a lot of redundancy, so that you really should have been doing lots of copying and pasting. So if you really knew what to do, this shouldn't have been too bad. That was my hope. So we start off, 75 ohm transmission line. We have a load impedance, 25 plus 25, and a center frequency of 250 megahertz. So what I did was just kind of set it up to walk you sort of step by step to create the Smith chart here, or this little Smith plot. So you notice we have a, first things first is we're just going to define all of our model parameters like we did before. So we have the 75 ohm impedance, then it was 25 minus 25, is that right? Sorry, I was toying with this, so I have to make sure my values are still there. Yeah, no, 25 plus 25, let's go back. There you go, so that's our load impedance. Here is our center frequency, and then our angular frequency, and so on. So first things first, you want to just calculate your baseline reflection coefficient. So the idea is, we have this really nice function that will calculate the Smith chart here. So everything is pretty much copy and paste from what I uploaded to Canvas earlier, right? And then we want to plot our reflection coefficient and our two little magic circles here, right? So we're going to highlight the magic. I really wish I had a better name than magic circle, but I guess magic circle will work. So again, you create just an array of angles, and then you plot a couple of circles, right? So there's a circle shifted to the right, there's a short circle shifted to the left, and then we draw a big fat dot representing our starting point. So that's what you should see for right there in the beginning. So let's see. So it says, yeah, so you're going to download that function, plot the baseline reflection coefficient between your transmission line and your load. So that's the big giant dot. So that's assuming there's no matching networks anywhere. That is this dot here corresponding to that. And then we have our two little magic circles. So I guess you could call this one is the resistance circle. It's a constant resistance circle, and it corresponds to a normalized resistance of 1. And then this is a constant conductance circle with a constant conductance of 1. So the main issue is, are we inside or outside these circles? So if I'm inside this circle, I have to pick either a low-high or the high-low. One of them will work, the other will not. And then if I'm inside this circle, only one will work, the other will not. And if you're somewhere out here in the space between, then you can actually pick either one and get solutions.
Okay. So this is where I have some confusion.
Yeah.
So you plot the initial reflection coefficient, and it's in the magic conductance circle. Now, page 229 of the text, it says to plot the normalized impedance. And if the normalized impedance is inside of the 1 plus JX circle, which matches up with your magic resistance circle, then you use the other network. So I have confusion there.
So I think what the book was trying to do was keep it simple, where they said, if you're inside here, you pick the one, and then if you're outside, you just do the other. And you didn't want to get bogged down with sort of the either ors in between. Because that it's like either of those solutions are both equally valid, so he just tried to keep it simple. But I went through, you can actually draw the circles, and you'll get solutions for both cases when you do that. So I think that's what Posar was going for, was just trying to keep it simple without trying to be like, if in here, then use X, if in here, then use Y, and then if out here, then pick one or the other. And I don't know, maybe maybe Posar just didn't think that bit through enough.
I guess that was my confusion on question 2, because in the YouTube videos, you drew the reactance circle, and you basically said that if RL is greater than Z naught, so it's inside the reactance circle, it's high-low. If RL is less than Z naught, then it's low-high. So if it's outside the reactance.
Oh, that was me just parroting what Posar said until I started working through them, and I realized, well, actually,
that's where I was confused, because and if it was on the reactance circle, then you could use either. So that's why I asked you the question of like, so I just assumed, I'm not looking at like the capacitance circle. I just looked at the reactance circle, and that gives you, the low-high.
So let's walk through that, because that's part of the circles that we're going to draw here to show that. So let's see. Hold that thought for another couple of steps down. So this is the picture you should have immediately for this problem here. So then we'll scroll down a bit. So the question, is it going to be low-high or high-low? So I deliberately picked it inside one of these circles or the other. So you have to commit to one or the other. You can't do both, right? So in this situation, if memory serves me correctly, which it actually doesn't, I completely forget which one is which. So yes, this one is going to be a, don't tell me, because if it's series, then that would be this circle here. So that's going to be a low high. Is that what everyone else got?
Yeah, that's what I got.
Yeah. So, because remember, you can either go along circles this way, or you can go along circles over here. So you imagine a circle where the left edge is touching that bit there. That is if I put a device in parallel. I can go along those circles. And if I do the series first, then it will be the circles way out here. So my goal is to intersect with either this circle here or with that circle there. So if I have the high on the end, so low high, that means I can traverse these circles and I'll intersect somewhere on this guy. If I do it the other way, I'm only going to twirl around here and I'll get nothing. So I believe I have you plot that specifically to prove the point. So create an array of reactances ranging from, you know, 1,000 minus 1,000 to 1,000, and you add them in series, and then we'll calculate a bunch of reflection coefficients. Yeah.
So when you did your two magic circles, you plotted them in black, but the question asked for you to plot them in blue.
Oh, did I?
Yeah, but then in question 3, you asked to plot the X values or B values in blue as well.
Oh, no, it says use black. Oh, no, sorry, hang on. So plot the reflection coefficient, use a black marker.
Yeah, and then it says make them both
blue.
make
them both blue. Oops, okay.
But then later on, you have to make another circle blue, so you end up with like 3
Oh,
blue.
okay. Yeah, my goal was to keep them separate. So let's make these black, and then we're going to do the other circles blue and red. Sorry, that would be a typo on my part. Well, it's not the end of the world because they'll stand out pretty well. But yeah, make them black. That was my fault.
So sorry to keep coming back to this, but Posar specifically states, if normalized impedance is inside of your resistance magic circle, thou shalt use a high-low network. We're doing a low-high network. So we're doing in contradiction of the text.
No, inside he's saying inside this circle, you must do a high-low.
Yes. If the normalized impedance ZL divided by Z naught is inside 1 plus JX circle on the Smith chart, then figure 5.2a should be used, and that is what we have defined as the high-low.
Let me see that.
And if you plot the normalized impedance,
we're doing a low-high right now. We're doing the opposite.
Correct, and
that's the right circle. The left circle's the different circle. That's the 1 plus JX is the right circle, which you're talking about. But the circle to the left is not 1 plus JX. It's like 1 plus JB.
Yeah. The 1 plus JX is the circle on the right. So if you are inside the right circle, that is a high-low. Is that what the book says?
Yes. And if you plot the normalized impedance, it falls inside of that circle.
Right. So that's when you do high-low. If you're outside of this circle, he is saying do low-high. So that's what we said. We must do a low-high because we are outside of that circle.
We've plotted the reflection coefficient, and it is landed inside of that circle. But if you plot ZL over Z naught, at least for me, unless I got something wrong with my code, it lands inside.
You said you plotted ZL over Z naught?
Because in the text, that's what Posar says to do to determine if you want to use a high-low, low-high.
So hang on. You said something a little fishy. So what page are we on here? We're
page 229.
229. There we go. Yeah.
Section 5.1, 3 lines down, first paragraph.
So there are what you don't when you plot ZL. You got to be careful what you're doing there. So I think you said something a little. Here, let's find a blank Smith chart here. So first thing, there's the normalized load impedance, and then there is gamma. Okay, so they are slightly different things. So I'm gonna put a little return here. We're gonna just run that again. So there is gamma naught, which you notice is negative 0.4 plus 0.35, right? So let's actually plot that on, say, the circle here. Or what you can also say is there is the normalized load impedance, which is ZL over Z naught. Okay, so you notice that's 0.33 plus 0.33. So the way you would read that is you go to, here, I'm gonna pin the video here. So can you see this? There we go. So there's two ways to do this. One is you can just plot gamma directly, or when you plot the normalized load impedance, it was 0.33. So you read out here 0.33, and then it was plus 0.33 again, which brings us to about here. If I can follow that a little bit. 0.33-ish, about there. So that took us there-ish, okay? Or when you plot gamma, you have a magnitude and an angle. So let's go back. I'm going to share my screen again, or I'm just going to calculate it on the side here. So gamma, if I do the absolute value of gamma, you get about 0.54. So what you can also do is read, where is this? Towards load. It says reflection coefficient, 0.5-ish. 0.54 is about that radius. And then you also need an angle. So you'd say angle of gamma naught times 180 over pi gives us 140 degrees. So where's my compass here? So you can actually say, okay. Sorry, I can't see my own. So you can, here's my radius. Right there, and you'll see how it will actually intersect that dot. All right, so we are over here inside the left circle. So the 1 plus jx circle is actually this circle over here. So we are not in that circle. We are way outside of that. So those are the two things, the way to plot. So when you plot your normalized impedance, you have to read off the impedance circles and then the reactances. You don't treat it as a complex number and plot it with a magnitude and a phase. That kind of makes sense? Is that where that confusion came from?
That's exactly where that confusion
Okay, we are not inside the circle. So those are two completely separate ways to get the same dot. One is just magnitude and phase of the reflection coefficient. So you saw I had the magnitude. You can read off right down here. There's the actual magnitude on this little thing here. And then the phase was 140 degrees. So you would actually, let's see, it starts here at 0. It should be, yep, there's 140 degrees. So if I go to 140-ish, like that. So this is actually a great exercise, by the way. So there's 140, it was like 142, I think. So that, you just draw that line. And so there's two completely separate ways to get the same dot. So I read the values on the circles as the real and the imaginary circles, or I just did the actual polar plot with a magnitude and a phase. So let's now go back to share my screen again. So that is our dot right there, and corresponding to that point here. So that was actually a good exercise in the Smith chart. So that ties into the stuff I was hoping to do later. So where the heck were we? All right, so that's our starting point. So now we'll go down. So the question was low, high, or high, low. We decided when we are inside that circle, it must be low, high. Because the series will take me along these directions here. So we'll see that now, that visualization in this next step. So create an array of reactances and add them in series, and then calculate the reflection coefficients corresponding to that. And then we repeat by doing the similar thing in parallel. So I'm just gonna delete that line. So we can add a series reactance or a parallel susceptance, and then we're just gonna plot the curves, right? So here's the series reactance, just X. You see it's a Lin space of minus 1,000 to 1,000. So you just pick some range. Ideally, it should go from like minus infinity to plus infinity, but it looks awful when you have to finitely sample that. And then for the susceptances, we picked some range and we're doing the same thing. So either this is a series impedance at the load or a parallel susceptance at the load, two entirely independent calculations, and then we're calculating the reflection coefficients that would correspond to each of those scenarios, and then we just plot. So you see this result. So this is why I did the red, blue, and the black here. So the red corresponds to a series reactance. I can go anywhere along that red circle if I add a reactance in series to my load. And then if I do the parallel susceptance, you see I go along the opposite circle. So this is why we have to do the series next to the load, the low high, because I can intersect with one of these circles in that situation here, okay? So just to sort of drive home that point a little further, what would happen if I started out here in the void? So I'm gonna make this something like 50 ohms, 55, and then I'm gonna make it plus 75. I'm gonna find a value out there somewhere. There we go, something like that. So you see, if you're out here in between, you have a choice. If I do a series reactance, I can intersect here and here on the left circle. But if I do a shunt susceptance, I'll intersect on this guy over here. So I think that's where Posar's reasoning came from, is he just wanted to keep it simple, because either solution is kind of the same either way. You need a capacitor and an inductor. It's just a question of whether or not they're in series or parallel. And they're both just little tiny chip devices at the end of the day anyway. So it sounds like he just wanted to keep it simple by saying, if you're inside over here, then just pick one, otherwise do the outside. But technically the full story seems to be, if you're out here, you can do either or. Because now I will intersect the opposite circle here. And if we go really high, something like 150, then that will fall in here. So now I have to be shunt rather than series next to the load, because now these red circles have nothing to intersect with. So you can imagine this red circle has to be big enough so that it can intersect over here in order for one option to work and not the other, and then vice versa. So does that kind of give a visualization? So that's why I think I have to disagree with Posar a little bit. He was trying to keep it simple, but it didn't feel like the complete story to me. Okay, so where the heck were we? We were at 25 plus 25, and we're there. So that's why I really love doing these little visual demos with MATLAB, because you can just play with the parameters and you see how the circles change in real time. So we're way over here. We have to use the low high, because that means we're going to follow the red circle first, and we're going to find our intersections with the far left circle over there. So that is what this step is trying to get you to visualize these two circles. And I really love, again, the whole point of doing that is now I can just play with the parameters like they're little knobs, and you just see how things move around when you just play with values in real time. So that is one of the things I love about doing stuff on MATLAB like that. And now you should have the code that does this as well for yourselves. I uploaded the thing on Canvas, I think, Monday or Wednesday, and when I did that, so feel free to toy around with it. Okay, and then, that's all I got at this point. So then, yeah, the homework we did on Monday, I gotta dig that guy up. So let me find that. So I put together my homework key, and then we did the thing in class, and the class solution turned out to be way better than my homework key. So let's use this guy here. So I think, yeah, this is now doing the same thing. So we said we had 75. So I'm just jumping now. This is the code that I uploaded for the class earlier. We'll do 25 plus 25 again. So you see, there's our starting point. So I'm not drawing the full circle with this particular code. So you have to make a couple little tweaks for that.
The frequency.
Yeah.
I was saying the frequency needs to be 250.
Yeah, sorry, I just changed it. There you go. So this is the rule according to Posar, is if you're inside here, pick one, otherwise pick the other. But it can, you notice I made a note here, both will work equally well if you're in the void between here. So by default, it just picks the one to keep it simple. So we create the blank Smith chart. So everything after here is going to follow the homework. The only thing I didn't do is draw both circles there. We're just going to kind of draw the contours as we go. So the idea is I need to calculate how much series reactance do I need to intersect up here or down here? So that was this function here, which I asked you to write for yourselves. So again, we'll just look at that, and you can see I did a nice little ASCII art here where I drew the networks. So you have a low-high versus a high-low, and it just follows the equations in Posar. So they're just the closed form solutions. You do the horrible mixing and matching between real and imaginary bits, and you get the two solutions, and you just grind on them, and a mathematical result pops out. So you see it will give me an X and a B, and then a little flag saying if it's high, low, or low, high for the results here. So that's all that function does. It spits out the two solutions. So I'm going to have an X that will correspond to this intersection and a B that will correspond here. And then we are going to unpack those values. So there's a B1 and a B2 and an X1 and an X2. So I think X1 corresponds to here and X2 corresponds to down there. So then I believe we'll scroll down here. So how much reactance or susceptance is required to intersect? You know, remember there's two possible solutions. So you have to give the two values here. So basically it's asking how much reactance do I have to add to intersect here, or how much reactance must I add over here? You notice I was deliberately vague because you have to tell me whether or not I'm adding a reactance or a susceptance. So in this case, these are reactances that we're adding. And the actual answer, according to my MATLAB calculations, which you can verify for yourself, so there's an X1 and an X2, that many reactive ohms, 10 and 60-ish. According to my calculations, right, which seem to work because you see how when you actually draw the contour, it hits the circle there. So that's how you know you've got the right answer. Then we scroll down, calculate the equivalent input impedance and the equivalent input admittance looking into the new circuit, okay? So that is just, if we were to draw this, so I'm gonna go back to my pinned video here. I'm gonna stop sharing. Oh yeah, we're pinned here. So remember what we have at the moment is something that looks like this. So there is a, sorry, I drew that terribly. There's a load here, and we have decided we must have some JX here. And there's two possible solutions. And if I'm looking down into here, there is some equivalent input impedance / input admittance here. Where, remember, this is just going to be JX plus ZL basically, because it's in series. And then the YN will just be 1 over that. So let's go back to my screen share. So that's what we're asking. Calculate the equivalent input impedance and admittance looking into that new circuit. And again, there's two solutions. So we're just going to call them A and B corresponding to the one and the other. You can see in my code here, I unpack them as 1 and 2, but you know, technically I should say like A and B or something if I want to be consistent with the homework there. And then you're calculating the new reflection coefficient at each of those values, okay? So the idea was indicate that with a little dot of some kind. So I didn't actually do that. But the idea would have been, where are we at this point? So we've unpacked all this. So now we're drawing the contours. So all I'm asking you is add a little marker at these two positions. I didn't actually draw that in here. I think I do that when I do my series and shunt stub stuff, but because you notice we're plotting that. So let's just do the last little bit. So basically what I'm saying is if you've drawn the contour, just put a little circle of some kind at the end. So do something like OR at the end. So we've created an array, but the last point in the array is the actual sample we care about. Oh, did that not draw? Oh, because we're not doing a high-low. This is a low-high. So we'll do it down here. Oh, dang it. That's the, the end of the second contour there. Should be up here then. There it is. That's what I'm trying to do. Just draw a little circle there at that little intersection point. That's all I'm trying to ask for. And then, of course, we'll do it again for the blue dot. We'll just do something like circle blue for the second solution, the B solution like that. There you go. That's all I'm trying to say is indicate that little intersection point there. So that's what it says. For each solution, calculate the new reflection coefficient and superimpose each coefficient under using black dots. Okay, so I said black dot, so that will be something like dot K instead. And then you give it a big giant marker size, like 40 or something like that. So there's my new dot. So just something like that to indicate it. I was a little overly specific there, but you kind of see what I'm going for. And then calculate the normalized impedance Z in and the normalized admittance for each solution. So in other words, there's a impedance and reactance kind of corresponding to that new point there. So that's just calculating the input impedance and you normalize it to the characteristic impedance. So that'll be some number there. And if you plot it, you should see it actually intersecting those circles there. So we don't have it here, but you would basically be reading off the Smith chart here, circles. That's one way to do it by hand. Then calculate the final component is needed to match the load. So just that connect the dot there. Indicate whether it's a series impedance or parallel susceptance. So now I have to add a parallel susceptance to go along this circle and take me to the center here. So, and then calculate the final component. So I guess by component, don't give me an actual capacitance or inductance yet. What I meant was give me the either the X or the B. In this case, there's some B value corresponding to that, and it has units of inverse ohms. So bear that in mind. And then finally, convert them to a capacitor or an inductor. That's the final thing. So remember, if I'm going a positive reactance, so we have two reactance values here, X1 and X2. So one is positive, the other is negative. So when they're in series, this will correspond to an inductor, and this is going to be a series capacitor. And then you flip-flop for your B's. Okay, so remember there's a positive and a negative. So a positive susceptance is a capacitor, and then a negative susceptance is a inductor. So just remember that. So series inductor will be a positive reactance. A parallel inductor is a negative susceptance. So it's just kind of getting all those ideas straightforward in your head to make all that work. So you have these X's and B's and just convert them to actual inductance and capacitance because you now have a frequency you want to match them to. And then finally, at the end is just suppose I change the load to something else entirely, right? So we're going to go all the way back here. And I said, suppose it was 100 minus 25, like that. So all I did was move it over into the other circle to force you to pick the opposite solution. So you're doing everything exactly. If you wrote code for this, you just have to copy and paste it all and just flip-flop the high-low versus the low-high, so you get the same sort of results. So all the inductors are going to be, all the series inductors become series capacitors, and then and vice versa, and the low-high is now a high-low, if that makes sense. So my goal there was you kind of write all of this code to go through these steps, and then finally you just use that same code to copy and paste, and you just change the order of a few things to get that new solution there. So again, since my MATLAB just calculated it for me exactly, you should get something like, oh, here's my two X's. So you notice I get about a positive and a negative. That's for my, the second half. So actually we got to start with it's a high-low, so that means it's the susceptance is coming first. So you notice I get a positive and then a negative. So if I remember correctly, this should be the positive and that should be the negative. Actually, I don't know that off the top of my head. Actually, I think this is the positive because red came first and blue came second. So you'll have to double check which one is which when you do that calculation. All right, any questions there so far? It's just, I want to walk you step by step by just these contours along the Smith chart here. So then again, first is it inductor, series, or shunt, and then capacitor, series, or shunt. Okay, and just for consistency, I think we'll want to say we have to pick and choose which one is number one and which one is number two now. So by convention, I was just going to hope to see I get the correct values here at the end of the day. So I wasn't going to be nitpicking on which one is the first or which is the second. So let's go back to our little circuit schematic here. So we're going to have a high-low for the second problem, which is going to look like this. So let's just decide now that this will be number 1 and this will be number 2. Okay, so you'll want series and parallel, and you'll have to fill in the blank whether or not this is a capacitor or an inductor and vice versa, and what actual value you're getting for that device. Okay, so this might be an inductor or it might be a capacitor, and this might be an inductor or it might be a capacitor. So just make sure you can fill in the appropriate values there. Okay, so where are we now? So that's all of that. And then, so a 50 ohm transmission line feeds into a 100 ohm load. Follow along to design a So this one, I basically am just having you do your lab assignment. So if you did your pre-lab or your theory section of your lab, that's basically all of this homework here. So you should have just done one and copied and pasted for the other, essentially. That was what I was going for here. So that's why I was a little rushed in the lab, because it's like you're just doing this for the homework already. So let's go back to, here's the code. So here is my lab 5 where we do the shunt stub design. Let me share the screen. Sorry. Actually caught myself that time. So the idea is, so this is what I put together when I did my shunt stub design. So again, we have 100 ohm load impedance, a 50 ohm characteristic impedance. And I think I worked through all this in class Wednesday, right? Because we did these little contours here. So we can kind of just walk through it again if you like. But the idea is, where are we here? So we're going through again, imagine some arbitrary length, calculate the equivalent input impedance looking down the line towards the load. So that's the series little length of input impedance. And then we're plotting that. So make note of your SWR circles. So we have the 2 intersections. Okay, so this is the big change is we're doing the calculation for the series stub. So I'm probably not going to test you on the actual series stub because I have never seen an actual application where it's been used. The shunt stub makes just absolutely more sense when you're using microstrip. So we're kind of doing the series stub calculation anyway, but the shunt stub is just, or sorry, we're doing the shunt stub, but the series will be there as just for the mathematical joy of it all. But the only difference between the series and the shunt is you're either intersecting with the circle on the left or you're intersecting with the magic circle on the right. So that's really all there is to that little bit there. So we're just calculating again. So it's, you notice it's kind of paralleling the previous problem where we did the lumped elements. You're just replacing the lumped elements with transmission line lengths. So in this case, it's already done where you're doing the 1 plus JX, right? So how much length of D do I need before I intersect here or here? Or equivalently, if I drew the other circle here, it would be how much length do I need to get here or over there? So there's a number of ways you could go about that. You could just calculate it by hand on the Smith chart. You could just create an array and just sort of zoom in on the sample that, or just try a little bit of trial and error until you get an answer. Or you can fill out the equations that were in the book, which is, what do I have here? So there's my L section matching network. There we go. So I created an actual MATLAB function that does the shunt stub matching network. And again, this is just grinding on the equations in Posar. So you can do it that way as well, and you will get an exact solution either way. So I'm not too picky on how exactly you come to that solution. All of those are perfectly valid ways to get there when you solve the actual distance here, D.
Quick question on that. Does that Posar equation, I've been writing the MATLAB function for that as well.
I'm sorry, I can only barely hear you. Can you speak up a little?
Yeah, 1 second here.
So I've got Posar right here.
Is that Is that
Yeah,
better?
that's much better. Thank you.
Okay. So the question I had was, don't we only get 2 values for D out of this equation?
Yep.
Where do we get the other 2 from if we were to do it?
Because you have the choice of a series stub or a shunt stub.
Oh, gotcha. Okay, that's right.
All right. So let's go ahead and draw that situation real quick, just so there's a kind of a picture to tie to this. So those are our 2 lumped elements. So the series stub solution, remember, is this sort of wacky arrangement. So this is your length L, and this is your D. So this will have 2 solutions for D, and then which will create 2 solutions for L. And then this situation over here, this is the shunt stub, where we put some little length of transmission line breaking off that away. So again, this is D and this is L. So you can see there's technically 4 solutions you have to calculate in total, but 2 will correspond to the series, 2 will correspond to the shunt.
Okay, yeah, that makes sense. I was trying to do 4 for one case, and that wasn't working.
So when you actually look here, so remember, for the shunt stub, you want to intersect the circle on the left here. When you go through, for the series stub, you're going to be intersecting the 1 plus JX circle. That's kind of the only major difference, which should make sense, because for series, if I'm adding a series reactance, I can follow these circles here. And if I'm adding a shunt susceptance, I can follow these circles over here. So I just have to intersect with the 1 plus JB circle to then have a path that takes me to the origin there.
Gotcha. Okay, thank you.
So I've got the shunts here. Where the heck is, there we go. So these are the 2 possible solutions for the shunt stub when you plot it. So you notice one goes all the way around, intersects, and it's nice and tight there. This one, because you're only allowed to go in the clockwise direction with these things. So I'm going to intersect and come all the way around over that way. Okay. So that's sort of what I'm going for with these, so that you have that picture of your paths that are allowed. And so there's a lot of overlap between this and the lab. And the only new thing here that isn't in the lab is the 1 plus JX for the series stub. But I don't feel like it's worth testing you on that. It's worth doing once just to see it, but again, I'd be very surprised to see an application that used a series stub rather than the shunt. Just, I don't know, maybe someone out there has done it. It just feels most of the time, at least especially in like the university setting, it's the microstrip is the nice cheap stuff that we can do everything with. So it makes the most sense to focus on that case. And then, okay, now imagine adding the series stub of length L. How long must it be to perfectly match? So you're just calculating the length L that will correspond to, this last little leg of the journey here. And then we do it again for the shunt stub. So I've got the solutions here for the shunts already, which is corresponding to that arc. And again, for series, it'll just be an arc over here instead that you're filling in. Okay, so then follow the instructions. So I think what I had you do is just hand calculations. Yeah, so is that what I did here? Let's see, explain what you see. Take note for the SWR circle. Or did I repeat myself? What did I do here? So we have a 50 ohm ZL, follow along. Here's our propagation velocity. So we create the blank chart, the default reflection coefficient. We draw the 2 magic circles, imagine some length L and D, create a bunch of values for D. Then we're going through this, calculate the lengths that correspond to the intersections. And now imagine, so it looks like I'm having you calculate, and then I have you, oh, okay, so this is just filling in the contour for there. So it looks like I just had you do the calculations, and now this is actually plotting the little contours there. Does that make sense? I hope. I think I worded myself, I must have been working on this at like midnight because there's some redundancy in what I put here. But so the idea was do the calculations and then just draw the picture associated with it. That's kind of what I was going for. So I might tweak that if there's any weird redundancy that doesn't belong. But you can see I'm just having you create the arrays with your solutions now to go there. Okay, yeah. So I had you do the calculations, just sort of filling it by hand. And now we're just drawing the picture to go with it. I think I did not realize I already had you drawing a picture here as it went. Yeah. So I had you create the blank picture here, but then everything else, oh, I had you create an array of D. Oh, okay. So they're slightly different here. So I had you so I think for the first part, I'm having you draw like the full little SWR circle, and then the second one is just focusing on the contours. So just follow the instructions, and you should get some pictures very similar to what I've got here. So yeah, I must have written a bunch of problems and forgot what the previous one did. So that's a little disorganized, but hopefully that makes sense. Any questions on that? Is there any confusion what's going on there? I think, yeah, what I had you do is draw the SWR circle and then the two magic circles next to it, and had you think about the intersections. And this one is just have you explicitly draw the contours corresponding to that. So that's all that's going on there. And that's about almost all the time we have. So I was hoping to do some practice problems with the Smith charts. But that's okay. We're saving those for next week anyway. So we'll work on that. Actually, we've still got a couple of minutes. I think does class end at 11:30 or 11:35? I think technically it's 11:35 is when we're done.
35.
Oh, good. I got you for 3 more minutes then. So that means I can correct my little boo-boo from last week. So we're going to do a very whirlwind Smith chart problem here. And if it's okay, I might go a couple minutes over, in which case I'm sorry, but you're welcome to leave. And this is all being recorded. So you can go over it later if you like, if you have to leave early. So we're going to stop sharing. So we're going to do this on a Smith chart. And I'm not going to brain fart in the last step this time. So just to reiterate all those same ideas. So let's say, I was even going to put together like a little recipe for you here. In fact, I've already written it down, so there's no point in writing it down again. So let's do that usual problem. Suppose my load impedance is 100 ohms and my characteristic impedance is 50 ohms. So this is going to be basically the lab assignment. Okay. So step 1, I wrote it here. Step 1 is you're going to calculate the normalized load impedance and plot it. Alternatively, you could just plot the magnitude and phase of gamma as well. So I'm just going to put plot gamma, or gamma sub 0 for the default reflection coefficient. These are the same thing. You can either calculate this guy and do the intersection of the circles, or you can just plot this guy directly. Those are one and the same thing. So in this case, my little z sub L is just this guy divided by 50. So I'm going to get 2 plus no reactance here. So all you do is you look on these little reactance circles, 0.3, 0.4, 0.5, 0.6, 1, 1.2, 2. And there is 0 reactance, so it is going to intersect right there. That is my default starting point for my reflection coefficient. So step 2, this is kind of optional, but it's a nice visual aid, is draw the SWR circle. So you take your compass here, and I'm just going to find this guy here. So it's just a circle with constant radius centered around the origin. This is a little harder than it looks. There we go. Like that. So that is, remember, that's called the SWR circle. Okay. So if we're doing a series stub, I would want to find the intersection going in the clockwise direction that would either take me here or to here. But since we're doing a shunt, I technically need to intersect on a circle out here over here, but they're not drawn on the Smith chart. So the little trick for a shunt stub, so this is step number 3, for a shunt stub, plot the dot at the opposite end of the circle. Or alternatively, what you can do is calculate the normalized admittance and plot that instead. These are the same operation on a Smith chart here. So all that means is I'm going to treat that as my starting point rather than here. Because you notice if I calculate my normalized admittance, it is 1 over little zl, which is 0.5, which incidentally corresponds to 0.5 plus 0. So that is a fun little trick, because now all of these constant resistance circles with variable reactance have now been transformed into constant conductance with variable susceptance, because everything just got mirrored and flip-flopped by the mere virtue of treating this as my starting point rather than here. That's the idea. So now step 3, well, that was step 3. Step 4 is find intersections with the 1 plus jx circle. Let me get that here. I need my intersection with 1 plus jx, and then I'm going to read off the wavelengths. So in other words, here is my magic circle here. In fact, I'm going to use a big fat Sharpie just to make it stand out a little more, because we did big fat black circles when we did this in MATLAB. I'm going to read that out here. There we go. So my intersections are going to be here and here. Those are the 2 intersection points I care about. So what you do, let's draw these in red, because why not? So you get the value. So using a Sharpie is probably not the best idea, because you can't see where it adds a little bit of error to it. So you can do about there. And then we're going to do another little point here. So it's about there, okay? So you're going to read off wavelengths towards generator, which if you come over here is 0.152. Then you come all the way down here and you just read it off, which is about 0.35. That is my wavelengths. So this corresponds to D1, and then this is going to, let's redraw this, 0.35. And technically it's D2 over lambda. Okay, D1 over lambda, like that. Because this is normalized in units of wavelengths. Okay, so that told me my distance D. So the final step, so remember in your head what we have. So I'm going to just kind of draw this here. What we've just done is we've created 2 situations that look like the following. So here is some length D. This is my load impedance, and this is some, Z naught. And what we've done is we've asked basically what is the input impedance looking down this little length of series line. And that brought us to this little transformation at these 2 intersection points. So the question now is, how much shunt do I have to put in here to give me a match? Okay, so looking down this line, you'll notice I have 2 normalized impedances here. This one is going to be, let's do this in green maybe. So I have 1 plus J, and this is, if I can read that, about 0.7. Okay, so that is a normalized load looking in. And this guy over here is going to be 1 minus J, 0.7 down there. So we'll call this like my normalized load impedance prime. Or you could put a D there to indicate the length looking down. So we'll say little z sub L prime there. So what you're basically asking now is, how much shunt susceptance do I have to add to make that go to 0? So what you do, this is the step I brain farted on yesterday. What you do is you just read this line here. Where are we at here? There's my 0.7. Like that, and that will just kind of go away. So these green circles are what we care about now, because the equivalent input impedance looking down any of these little shunt stubs will correspond to a plus or minus 0.7. And since everything's sort of flip-flopped, this plus is actually a minus because we're in the susceptance world. and this is basically a plus. So things are getting sort of backwards. But the way it works now is you just say, okay, I'm going to draw one last line from here to there, and corresponding to this one, that. So that makes, so I have to read over here to get my last little bit of wavelength for L. So this is going to now read this way. This is my L1 to get to here, and then you go all the way around to here to get your L2. All right. So the idea is actually, if you want to interpret it intuitively, you can imagine that you're basically starting here. You imagine I'm looking down an open circuit line, which is now being flip-flopped on the left, and I'm asking how far do I have to go along this before I hit that exact value there. And then they negate each other when I put them in parallel. And then of course there's another one that's going to go all the way around this way. So you're going to read off. Notice this is, now you have to read this on wavelengths towards load for this particular case, because things are backwards in this case. And so what I'm going to get is 0.402 wavelengths. So that is my L1. Then you come all the way down here, and I get, what do we get? 0. So it's 0. Oh, sorry, I got to make sure I read the inner one here. So it's 0.1, except that it's decreasing that way. So it's not even that. You have to say 0.09246. So 0.096. So you have to read the inner wavelength number there, not the outer, which is what I did here. Okay, so to summarize, I had D1 is equal to 0.152 lambda, and then a D2 was 0.350 lambda. And then I had an L1 correspond to this, 0.402 lambda, and then L2 is going to be this guy here, whoops, excuse me, which is upside down, so 0.096 lambda. So that last little step is what I messed up. So if we now go back into MATLAB, this will actually match the results we got. So I'm going to do a quick final screen share before we're done. So let's see, we are doing our shunt stub matching network. One of these is my, there it is, lab 5. Okay, so this is just using closed form expressions to create an answer. Okay, so you notice I have two distances D and two lengths L. So what should happen now is I said D1 is my wavelength, which was L0, times 0.152. So if I hit enter, this should correspond to that length there. And you see it matches out to like 3 digits of precision. And we'll do the same thing for D2 is my wavelength, which I calculated times, and I look at my answer, 0.350. So that should now match the analytic solution here. And you see it's off by like a little bit on the 3rd decimal place, and that's okay. So the same now, we're going to do L1 is going to be 0.402 times wavelength, which should now correspond to 0.0663, which would nailed it just fine. And then L2 is now 0.096 times wavelength. And again, didn't quite, it's off by a teeny bit, 0.162 versus 158. So it's close, but not quite. And that's what we expect when you're doing this stuff by hand. Okay, so just gonna put this here. So I'm gonna stop sharing. So here is the recipe that you'll want to write down at some point. You're gonna do this for your homework next time. So this is just for the shunt step. Step 1 is you calculate your normalized load impedance and you plot it, or equivalently you're plotting the reflection coefficient here. This is a little easier if you're doing it by hand than doing a magnitude and a phase, but take your pick. You can do that in MATLAB or on a calculator and get the same result. You're going to draw the little SWR circle. So again, we started here, we drew this little circle around here. Step 2. Step 3, if you're doing a shunt stub, you have to do this. You're going to draw a dot at the opposite end of the circle. So instead of using this as my starting point, I jump to the opposite end of the equator, and then I use this as my starting point instead. So that changes all of this into admittance space rather than reactance, or impedance, I should say. Remember, equivalent, you can also just calculate the normalized admittance and treat that as your starting point as well. Those are 2 equivalent steps. And then finally, we're going to calculate the intersections with the 1 plus jx circle. So here's my 1 plus jx magic circle, and these are the 2 intersection points I care about. And then you read off wavelengths towards generator. So you see how I created, there you go. So you draw your line out to here, and you just read off your wavelengths towards generator. There's your D1. You do the same thing on the bottom. Sorry, it's hard to frame this thing in the camera here, so I apologize for having to keep moving this around. But you can now see I go down to here. That's my D2. That's step 4. Find those intersections and you read off your wavelengths. Step 5, read the value of the reactance circle. You're going to have 2 reactances, X1 and X2. In this case, you'll notice it was plus and minus 0.7. That's the green arc here. And then I have this guy over here, okay? And then finally, you're asking how much shunt susceptance do I have to add to negate them? And so that means you just simply read off this little wavelength here because you're basically following the SWR circle for an open circuit now, for an admittance. So you just read off wavelengths towards generator here, and that will give you your L1. And you see down here, you read it off, and there's your L2. And that's it, then you are done. So that is the recipe for the Smith chart solution. And it's pretty quick and straightforward. And like I said, I kind of have mixed feelings about it because you want to have that intuition of how things traverse the Smith chart. But I hate the idea of doing stuff like this by hand when we have computers who will do the heavy lifting for us. But it is something that you'll need to be comfortable with, especially when you go into microwave engineering part 2, if you're going to take that in winter from Dr. First. Another thing I kind of realized I hate about doing these Smith chart solutions is they tell you nothing about bandwidth. So if you want to create a frequency response, you can't do it on this, not unless you want to do it by hand for like every last frequency. So that's another one of my personal kind of rants against Smith charts there. But it is just one of those things in microwave engineering you do need to get comfortable with, is reading off these values here, especially if you're going to take the next class. Okay, so that's the step-by-step. So when you take a picture, basically I want to see this picture here. And here I'm going to lower something like that. So when you turn in your result, basically it'll be something like this. You'll want to snap a picture and then maybe rotate it 90 degrees for me. And so as long as I just see these basic steps here and your lines are corresponding to the correct little points here, then that's what I'm after for that homework assignment. So just snap a picture and submit essentially this right here. So you want to see the starting point for your reflection. You'll want to see these little radial drawings corresponding to each little point in this particular design problem. Maybe highlight this circle if you want. You don't necessarily have to, but at least these intersections, you'll want to make some kind of note of them as well. Those sorts of things. So as long as it's very clear what's going on, then that's what I'm after. And you could probably even clean it up a smidge. You don't necessarily have to draw all these little scribblings around here, but that's kind of the idea. All right. So I won't be too much of a stickler for that because there's no right or wrong kind of answers there, but that's the idea. Okay. So hopefully that was pretty straightforward. And again, we'll do some more of this on Monday. I'll probably do like one more walkthrough again on a different problem just so you can see it. And then we'll do like the binomial matching and that kind of stuff. Okay. So unless there are any questions, that's all I have for today. And thank you for sticking around. I'm sorry to go a little late, but again, if you left early, this is recorded now, so you can follow along later.